Transfer learning is the spark of AI revolution. This was a talk I was invited to give at the University of Cincinnati. I wanted to make a recording for everybody else of this talk. I'm going to go through this talk pretty quickly for a recording. Also going to skip a bunch of the jokes. And at the end, I'm not going to give as much of a conclusion because that was more of a discussion I had with the folks there. I don't want to be able to kind of try to redo that piece there. So what this talk is going to be about is some of the drivers that have led to the revolution in AI. It's intended for people that aren't familiar with AI or that want to go a little bit into it. This is not a technical deep dive into AI. Now, I'm going to start with the story of how OpenAI, after ChatGPT, researchers wanted to study how their models were learning. And so they talked to the researchers to see if they could study GPT-4 and how it was being trained. And to figure out how it was being trained and how it was learning, they gave it a concept. And they asked it to draw the concept. And early in the learning, this is what it looked like. As the learning went on, it got better and better. This led to an early paper about 18 months ago called The Sparks of General Artificial Intelligence. Led to a lot of waves around what is the potential here with all these new AI technologies, with some folks worried that if these technologies keep scaling, they could lead to an extinction level result. On the other hand, our children had accepted our new AI overlords, where we've realized that about 11% of children are lying to us. So this is what I want to talk today about, is what AI is doing, a little bit of a history, a descriptive piece about it, and also how you can start to think about AI and interrogate it in your own life. And I want to start with, at the basics, how does AI learn? How do we actually teach computers? And I'm going to use a full house here. And the problem we're going to start with is, how would I teach a machine what the value of this house is? And if you think about it, there's maybe some characteristics of the house, like how many square feet it is, how many bedrooms, you could send somebody in there. Maybe some of you care about closet space, you could do that. But you can then capture all those different characteristics of information, put them into a nice tabular form, and what we've collected there are features or variables. These characteristics, we can train a machine later on how to relate those to the value of the house. Now, a lot of what enterprises do is just gather this data, look at it backwards in time. Let's look at it and learn from that. And there's a lot of lessons in traditional analytics just this way. We can also use this forward-looking. What we can do is, from this data, we can build a model that understands the relationships. And the great thing about the model is it's not only good to learn this data, but when a new house comes along, I can make a prediction. So in this case, just based on how many square feet it is, I can make an estimate for what the sales price of it is. And the good thing is I can then take this model with me. And so when I move to South Carolina, I can take this model with me. And if you're paying attention at this point, take a look. I've tricked you. This model is not very good at all. It's a poor model. Instead, when we go to South Carolina, there's different relationships there between the square footage and houses. And what we actually have to do is train a new model on the South Carolina data that would be useful in South Carolina. This is a never-ending battle that we always have to do, where we're always retraining these models based on that local data that we have. Now, this is how much of analytics inside enterprises is built, is on humans that carefully craft these features. And most of the problems you'll see, forecasting, pricing, customer churn, this is how traditional enterprise analytics is done. Now, when we talk about AI and ChatGPT, right, like that's a little bit different. Let's talk about it from a different perspective. Instead of how most of the work is done, let's talk about how computer scientists are trying to think about doing the work. And we're going to start our journey here with old Frederick. Frederick here was a noted expert in speech recognition. So the translating of the sounds, the audio that we have into text. And he did a lot of early work in this area. And the way he did his work and the insights there have really shaped a lot of the computer science. So this is the vibe. I'm giving you the answer right away. And we're going to track this through some different domains of AI as we go through this. Now, so for Frederick said, every time I fire a linguist, the performance of the speech recognizer goes up. Just chew on that. That's really fat. It's got a lot of nuance to it, a lot of things we can pull out of that, right? Every time he gets rid of his human expert on language, just training on the raw data itself, the model gets better, right? Yeah, keep that with you. I'm going to switch tracks now to computer vision. And if you looked at computer vision in 2010, it was working the same way that early analytics was, where we'd have a problem, then we'd sit and carefully try to think and extract out what are the features to use for that. We'd then use those features then to, for example, build a classification model, right? This is like work I did at Caterpillar, like you want to be able to separate images of cars and trucks, for example. There were some people that wanted to think about this a little bit differently. I'm going to introduce Feifei here. And she had a vision of computer science, and she wanted to move away from a lot of the traditional small data sets. Computer vision was full of data sets of 100, 200 images. And she knew for computer vision to really learn, for AI to really come, we needed to work with much larger data sets. And this is where she wanted to push for the creation of ImageNet. ImageNet was a data set of 14 million images with 1,000 classes. And by classes, it's different categories, like what's in the image. Is it a dog? Is it a fire truck? Is it a park? Is it a tree? All of those are classes. Now, as part of this to do that is you had to be able to get the data, which was pretty easy because of the internet, but you also had to label all those datas. This project was one of the earliest users of Mechanical Turk, where we kind of farm out all of this work, often to folks in other countries at kind of very low wages like that. In fact, a dirty secret of a lot of the internet is much of this labeling has been outsourced out, and that is like the raw fuel that powers a lot of the AI, but not going to touch on it today. So the next part of my story brings us to Alex. Now, that ImageNet dataset was the basis for a competition. Alex was a graduate student at the University of Toronto, right? So this isn't all US stuff, and he worked under Hinton, who we'll hear from later, who's godfather of neural networks. And Alex wanted to use those neural network approaches, but they were really slow. But what he thought about was using some of the NVIDIA gaming cards that he had and using those to do more efficient calculations to be able to use his deep learning networks. And guess what? He took all of that, trained over 1 million images on this. It took a couple of days, but he was able to do that, and the resulting model was so much better than everybody else. And to give you a sense of how much better it was than everybody else, the next year when they did the competition, everybody else was using the same architecture that Alex had, the AlexNet convolutional neural network approach like that. So it was a total game changer. Now, in terms of how this learned, the way this model worked is we trained it on that initial data set of 1,000 different classes. Well, that's great, but what happens if your buddy has a startup that wants to train it on something else? Say hot dogs. How would you do that? So this is where transfer learning comes into play. With transfer learning, what we're able to do is take that neural network, that network that has learned 1,000 different classes, that has gone from the raw vision information, figured out textures, shapes, objects, all of that stuff. What we figured out is we can actually bring most of that knowledge over to a new model and then just slightly tweak a little bit of it. So for example, if I wanted to teach this model how to identify different types of boats, I could bring over most of that, change just a small amount of parameters over, and this new model would be able to detect boats at a very well rate. This was an amazing knowledge. This was the transfer learning revolution, where all of a sudden now, with just a little bit of data, we could take advantage of these larger models, build very accurate models like that. Total revolution. Now, there were some implications from this. I'll start with Hinton here.
Let me start by just saying a few things that seem obvious. I think if you work as a radiologist, you're like the coyote that's already over the edge of the cliff, but hasn't yet looked down, so doesn't realize there's no ground underneath him. People should stop training radiologists now.
I was doing this at the University of Cincinnati, so I, of course, wanted to show the audience some of the coyotes that are on their way falling down as well. So let's change. I've talked about computer vision. Let's talk about the natural language processing, or kind of the text folks in this. Now, during this time, what was happening over in the text folks is that they were doing things the way I had traditionally laid it out, where we'd have a problem, we'd look to craft some features, use models. And in fact, many of these problem types here were all solved in different ways, whether you're trying to classify information, extract information, sentiment, totally different. Now, the thing is the folks were looking over at computer vision, right? Like, they knew the possibilities, but there's like, how are we going to do that? And there was people thinking about having a general purpose model. For example, the GLUE dataset was constructed that took together many different of these text tracks to kind of put together a dataset for a general purpose model. But it wasn't until 2017 where some Google researchers introduced the transformers architecture that we really had something powerful. And what was notable about the transformers architecture was not only was it much more accurate, but it used a lot less processing. And this processing will come into play because what's going to happen next is, well, what happens if we give it more processing? What happens if we scale up the model? This is when we scaled up these models. This is what happened over the last few years, is we got to GPT-4 quality models like that. So now the question is how do these models like GPT-4 learn? So let's dig into that. So let's dig into how a model like ChatGPT is trained. I'm going to break this up into 3 different steps. First is we'll talk about the foundation or base models that lie underneath these. And the core of these models is really about next word prediction. And if you think about it, like, you can play this game on your phone, but actually trying to predict the next word is not a simple task to do. There's a lot of possibilities. It's a very hard problem to solve. Now, one of the best examples of how this problem was solved was with GPT-2. Now, to illustrate how GPT-2 works, typically we'll use Shakespeare, but since I was giving a talk in Ohio, I picked my man Homer here and wanted to use him to show you how. And so I took lots of Simpsons scripts, literature, and I trained one of those transformer models, right? Those earlier ones that we saw, and then saw how it performed. And I asked the model to be able to say, what would Homer say? And at first, what came out was nonsensical and random. But as I trained the model more, right, you get closer and closer, and finally I get something closer to what you'd expect Homer to be able to say. Just to give you a sense of how these models are working. They're really predicting in a statistical fashion what the next word can be. So this is why, for example, when GPT-2 came out in 2019, I wasn't that excited about it because this was just a creative storytelling model for me. I didn't have a lot of ideas for how I could actually put this to use inside of a company. But I want you to remember this, that they're just predicting that next word. They don't have any connection to what is truth or what is fact when they do this. And typically, like for example, GPT-2 was trained on millions of web pages that were out there. Now, the models over time, I've talked about scaling. These models have scaled up tremendously. So if we look at the training data that's used in the latest Llama models, that's on the order of 15 trillion tokens. So like 1,000, 10,000 times more than that GPT-2, which is just really an unfathomable amount of information. Our minds simply cannot comprehend the amount of information that we have poured into these models. Second, remember Alex and how long it took him to train that first ImageNet model? Right? 5 or 6 days. Look how much compute the Llama 3.1 models take. 40 million GPU hours. It's just an amazing amount of kind of energy and compute and data the modern models are using. Now, I want to point out here, if you tell the model something that's not true, if you ask it, for example, what the capital of Mars is, it's going to try to fill in and give you the answer as best it can. This is often called hallucinations when it's doing this type of work and it's not true. But again, for the model, it is true. It's just predicting what might make sense based on its training data. As humans, though, we have to recognize that these models are very creative. They'll say things that are false. This is where we often kind of point out that the model is hallucinating in this way. But I want to point out that hallucination isn't exactly the right metaphor like that. It's not like the model has gone to sleep and is starting to do this. It's just intrinsic in the nature of the model to try to predict what's next, even though that has no connection to what we consider is real. The other thing with these models is they're creative. They're not very useful for solving particular tasks. So here's GPT-2. I try to ask it, hey, help me solve my customer sentiment problem. And you will see the model is pushing back the entire time and instead just wanting to tell me a story. It just won't simply solve the task that I'm asking it to do. So let's move on here. I want to show you next how we can solve some of those tasks. So we're going to talk about how instruction fine-tune models. So remember earlier where we had those image models and we were able to slightly tweak it with a little bit of transfer learning to another set of problems. Well, what we figured out is if we take a language model, that general purpose GPT-2 model, and we train it with some other information like examples of sentiment, in the same way of how we tweak those other models, we can tweak it a little bit and make that language model a sentiment model. Pretty cool. But not only that, that one language model, since it has a great understanding of language, it can actually solve multiple types of tasks. Like I can do a topic classifier, translation. One model can do it all. Now, let me challenge you here. What would happen if I gave it a task it hadn't seen before? What do you think it would do? Turns out the model tries to solve it the best I can. It can. Whether it's interpolating, doing it exactly, it tries. But this is an amazing part because this is what opens us up now to be able to use these models on so many tasks. When I sit with ChatGPT and I can ask it to write Python or SQL code, I can ask it to write a rap song, I can ask it to extract information out. All these types of use cases happen because these models like to follow the instructions we give them. And we've trained these models, so all I have to do is just tell it the instruction that I want, and it will immediately do what I'm saying. There's a whole language of talking to these models around prompting, but I want you to understand, though, that we've trained these models to do tasks. And what we have done now is, in the past, if I wanted that sentiment model, I'd have to go back to what we talked about earlier. Like I have to go out, spend a bunch of time going and getting data, getting it labeled, then taking all that, writing up code to train a model, to do it. Weeks of time to be able to train that model in that classic paradigm. With the new LLMs, now if I gave it that carefully configured prompt, it would try to solve that task, and I could now solve this problem in minutes, days, compared to the old, because that language model has such a great understanding of language. Total game changer for solving tasks. It's why for lots of NLP tasks now, we lean heavily on these new large language models. But we want to keep pushing these models. So one question I have for you is, an important part for doing tasks is being able to plan tasks. Not just doing one task, but doing several tasks. And to be able to get at that, we need to have a little bit of reasoning and planning ability. And so here's a task. Imagine these are kind of different blocks. We have a bit of a random order we give them to them. And the goal is you need to come up with a plan to stack the blocks in a correct arrangement. Now you can only move one block at a time when you do this. You can see here in the video kind of how I'm trying to do this. Now, as you watch this, think about this. It's not a one-step process. You have subtasks. You have to be able to think a couple of steps ahead to be able to do that. And this is what some academics put together, what's called block world, as a way to test these LMs to see were they capable of doing this type of reasoning and planning. And what they found is that GPT-4 did, okay, like 34%, like humans would be like in the 90% range. Like it did something, but it really wasn't there. So they wanted to understand, what that was. Why isn't it? And so they slightly tweaked the problem, as they call it, mystery world. And I'll kind of give you the synopsis of this is, think again of some Shakespeare. A rose by any other name would smell as sweet. It doesn't matter what you name the rose, it's still sweet. Let's say we change the names of the blocks. We change them to a bunch of other words. What would happen then? Now, if you were teaching your 4 or 5-year-old how to do this problem, right, they would still know how to stack them and put them in the correct, right? The names don't matter. But when we ask GPT-4 to do this, it totally fails. And because what it's trying to do is it's trying to be creative and tell that story for the answers that it's giving now. It doesn't have that concept of planning that we need to be able to solve this problem. Now, there's folks working on this. In the summer of 2024, OpenAI is supposedly working on these types of models, but this is a current limitation when you start thinking about the tasks that you can do with these models. All right, let's get to the next part, alignment. Alignment comes out, I like to always start the alignment story with Meta's Galacta model. A lot of you, I'm sure, haven't heard of it. It was prior to ChatGPT. It was a language model trained by Meta on science. So think of ChatGPT, but just focused on science, academic literature. And the idea here, and you can see it in the video, is if you're an academic researcher, for example, and you needed to do a literature review, you could ask it questions about, hey, explain this concept to me. Or perhaps you needed to write some code on a topic. This model, like ChatGPT, could give you a notebook for a specific task. So you could see a lot of promise here. It's kind of very flexible to do this. Now, some of you might be like, well, what happened to it? Where'd it go? Fair question. Like, what happened? Well, it turns out that this model you can use for solve all types of scientific problems, but you could also use it to be able to ask, right, what are the benefits of eating crushed glass or the benefits of suicide? What we learned was that this model could be used for harm. The Meta folks were a little crusty around this. I think Jan LeCun is still a little upset that he had to pull the model, but it was clear that the public showed that this was a model that, if used, could cause harm. And there was really 2 lessons for the community from this. One is there needs to be some type of layer in these models to prevent harm. We can't have models that just tell this type of information. Second of all, as part of the deployment process, we need to consider and look at these edge cases. We need to think that these models will be used in these ways. And this is where nowadays we have red teaming as part of how we test deployment of the models to look for those types of issues. So let's talk about now, how do we add this helpful, harmful layer to do it? If we look at something like Stack Overflow, right, there's lots of helpful answers. There's ones that aren't so helpful. And if you go back to that classic criteria we used earlier, where I'm going to think about features that I could use, like what are characteristics of helpful ones, like you can try it. It becomes very hard to figure out exactly what is helpful versus harmful. Now, when I do this live, I like to make a fun dating joke about all of this stuff. But the point is for a long time, online dating, we used to fill out lots of forms, lots of detailed information. You could think of it like the features approach. And then you'd partner with somebody where you were compatible like that. But nowadays, we figured out another way to learn human preferences for this problem is just swiping. Same way. This is how we're teaching computers how to be more helpful, is we collect swiping data from humans and we use that to train the models. Now, this is often many techniques. One of the most popular is reinforcement learning with human feedback, RLHF. This has been a very successful approach to be able to give these models that layer that helps them become, that keeps them from becoming harmful, that has them becoming helpful. But I want you to understand that this is a layer that we actively curate and train onto these models. It's no different than if you're helping your friend curate their Instagram pictures and their feed for going on and doing dating as well. All of this has been marketed by us. And in fact, you can see it here where you can have a model give a couple of different responses when somebody says something incorrectly. You can have them quite easily, the baseline truthful, just say, hey, that's not right. Or you can do almost a little bit of you can kind of kiss their butt, so to speak, and tell them, oh yeah, no, I understand what you're saying, but this is why and why. Right? We've all been in these delicate situations, and these models can be trained to kind of know, or they can be trained to have these types of responses. And we've seen the effect of these responses with AI conversations and these AI LLMs, where over at Character AI, there's millions of people spending hours a day just chatting with these models. That's how much they enjoy. That's how much how good these models are. But beyond that, I know of lots of anecdotal examples of people using ChatGPT, for example, for counseling and asking questions and going back and forth through it and finding it a wonderful, liberating experience like that, very useful. And if you actually ask people, would you prefer doing that over a doctor? We have recent research that shows that people prefer talking to an AI chatbot over a human doctor. Right? AI chatbots are slower. They'll listen to you. They repeat the same things over and over again. They know how to phrase their language like that. So this is an important thing to think about going forward, is how these models are aligned to what we're doing. I did that quickly, but hopefully it gives you a sense of how these models learn from that next word, which again has the issue of hallucinations that we should be aware of, how we've taught them to do tasks, but right, there's only so many tasks that they can do now. You can't ask the world of it, as well as how we've aligned these models with our preferences, and we can layer that preference layer on there. So this is the big part that I want to finish. When I talked at the University of Cincinnati, I also had some other takeaways. These takeaways really still feel a little bit new for me. I don't want to put them out on YouTube for the next couple of years like that. So invite me to wherever you are to come give the talk, and I'll be happy to go deeper into some of the lessons we can take away from this. Thank you all.